Those who study quantum mechanics realize the world is genuinely a quantum place, such that all technologies are subject to the laws of quantum mechanics, not simply the classical approximations as were once described by Newton, Kelvin, and Clausius. Much of quantum research so far has been invested in computing and information technology, including banking and cryptography, for securing global financial transactions. Computing is very interesting with respect to quantum mechanics, as it showcases the entangled particle, one of the highlight reel aspects of quantum mechanics and one of the most curious. Meanwhile, in Europe, Farkaly and his group are working to describe quantum mechanics at the more macro level, in salts, even in biology, living examples of quantum biological traits being recognized in photosynthesis and in the curious navigational capabilities of migratory European robins. In the USA, outside of the program to perfect quantum computing and employ it on a larger scale, perhaps the most relevant subject in quantum mechanics today is quantum energy science. Currently, classical physics described batteries are the hope of the electric car revolution, yet decades of research have yielded no massive gains in battery science. The material science just has its limitations in a classical sense. What is truly revolutionary is the application of quantum mechanics to energy science, and energy storage in particular. Storage being the building block of sustainable transportation infrastructure, as well as a sustainable power grid structure. So let's try to understand how quantum mechanics plays a major role in energy science. First, we must realize that the electron can only be described quantum mechanically by its four quantum numbers. They are the principal quantum number, the angular momentum quantum number, the magnetic quantum number, and the spin quantum number. In an atom, no electron can share all four quantum numbers identically with each other. Each is therefore discrete. Now, this was totally unknown and remained unpostulated throughout the machine age, when all our current machine cycles were invented, from basic mechanics to refrigeration to analog electronics. Engines are classical, air conditioners are classical, CRT televisions were all classical, and none were particularly efficient. However, they worked, and thus classical physics was sufficient to satisfy for human needs and desires for robust mechanized transportation, land, sea, and air, various HVAC systems, and primitive electronic entertainment. But what about Farkaly's highly publicized study into the quantum nature of some salts? What was significant about salts not being able to be adequately described classically? The following is what is truly significant about that, and it really opens up a whole new way of thinking about energy science. Remember that electrons in an atom are discrete in at least one of their four quantum numbers. Now, we also know that salts have quantum properties, according to the latest from the European research community. How can we combine quantum mechanical properties in new and revolutionary ways to achieve something far beyond the limitations posed by classical machinery? I will describe the latest patent in quantum energy science, one which has been in progress now for about a decade already, as it is so difficult to describe to someone only trained in classical physics, and that unfortunately includes most patent examiners. But persistence pays off. What we were trying to achieve was a system in which electrons in more than one quantum state could be utilized for work. This then became the obsession. What types of work actually resulted from electrons in different quantum states? Well, it appears that such a dichotomy exists when a molten salt is used as a direct heat transfer fluid compared to when it is used as an electrolyte. We know how both of these mechanisms actually work. Electrical current flow involves electrons migrating from atom to atom, beginning in an electron-rich environment and arriving in an electron-needy environment, anode and cathode. Band theory states that these electrons are above the Fermi band gap and are free to move about. Concurrently, in semiconductor theory, electron holes move opposite the electrons. Now, everyone has seen animations of electrons moving in a flow of electrical current, but few have seen precisely how electrons get involved with heat transfer. Now, there's four principal thermal energy carriers: phonon lattice vibration, photon, fluid particle, and electron, as described in the textbook Heat Transfer Physics, published through University of Michigan, Ann Arbor. It's the direct comparison between the electrical energy carrier mechanism and the heat transfer mechanism at the quantum level that is the key to understanding quantum-based energy storage. Heat transfer is made up primarily of a squeezing motion, a concertina-like effect that moves thermal energy like the squeezing and releasing of a concertina. The electrons involved are principally valence band electrons residing just below the Fermi band gap. Photons and phonon vibrations are also among the principal thermal energy carriers. So we can understand that using a molten salt electrolyte as a quantum fluid is very convenient, as it supports both of these quantum operations, conducting DC current when used as a highly thermalized electrolyte and as a direct carrier of thermal energy. We know how both of these work, as for many decades we have used molten salts as electrolytes in pyrotechnic activated radar proximity fuses, and we have used molten salts as direct heat transfer fluids in breeder reactors as well as in nuclear machinery of all sorts. What we didn't realize at the time was these jobs were the direct result of electrons being in two different quantum states. So how does this help create a quantum energy machine cycle? Simply by first thermalizing the quantum fluid to a rather high temperature, say 800 degrees centigrade, and then forcing the electrolyte between banks of anodic and cathodic material. This creates a very high amperage electrical battery from which DC current is directly taken. Simultaneously within the exact same heat exchanger that houses those battery elements, we also have a plethora of gasifier tubes, these being surrounded by the molten salt, in this case acting as a heat transfer fluid. Rankine cycle working fluid atomized and pumped through the tubes will instantly gasify and be prepared to readily perform Rankine cycle work. The quantum nature of the device is noticeable when both happen at the same time and result from the same thermalization event. In the case of the quantum machine, heating is not accomplished by burning fuel nor by radioactivity. It is supplied by microwave energy and transferred to the molten salt by means of a patented interface material called the permanently permeable matrix residing inside a resonant cavity. Thus the heating is electric, not a result of burning any hydrocarbon mixture, nor the thorium heating of the late 60s MSRE reactors. Microwave heating is extremely efficient and is purely electric. What this enables is the use of the DC output from the cathodes in the heat exchanger to be voltage modified via switch mode and reintroduced to the input of the resonant cavity magnetron responsible for the thermalization of the molten salt. Now, for the first time in history, we have a truly quantum machine cycle. Electrons in two quantum states, each providing their own specific work product in their own novel system, producing electrical current and transferring heat. Since these are not the same electrons doing both jobs, we now have achieved the true quantum machine cycle. Now this is poised to be revolutionary, as suddenly extraordinary consequences arise regarding potential and achieved efficiencies. These efficiencies are not adequately described in classical physics and in classical thermodynamics. When we combine the two cycles together advantageously, we call it bootstrapping, or extending the discharge equation of an energy storage system by feedback of one of the quantum aspects to the other, thus totally altering the shape of the discharge equation from a Markov chain, typical waterfall shape, to a greatly elongated stair-step shape. Quantum physics and thermodynamics has thus reinvented the machine cycle. It is no longer necessary to extract work products from electrons in a single quantum state, as has historically been the case. This is absolutely revolutionary with respect to transportation, creating essentially the quantum battery, and also enables such varied machines as compressorless HVAC systems and combined power grid systems, in which a single central nuclear power source can be routed to a dozen local wind and solar power stations and their output currents combined in a magnetron to thermalize the energy storage media. This results from the magnetron utilizing a high voltage but low current source and a low voltage but high current source. Thus central and local power are ideal for providing these combinable inputs. In transportation, the quantum battery extends the initial charge storage by fundamentally altering the discharge equation itself. This is the elegant solution to portable energy storage, Instead of making classical physics batteries larger and bulkier, or trying to eke out chemical reaction efficiencies with fragile graphene barrier materials, someday promising to make lithium-air batteries practical, the quantum battery completely outclasses the classical battery with its fundamentally altered discharge equation. No classical single electron state battery can ever compete with a quantum battery. Just like no digital computer, no matter how vast in scale, can ultimately compete with quantum computers, simply because the computational matrix itself, the logic is fundamentally different. Quantum energy storage and the quantum heat engine are the obvious products of the recognition of the individual states of the electron, the results of the summation of Schrödinger wave equations for each particular state. Why this is so critical is recognized immediately by Maxwell's laws of electromagnetic energy as a two-component force, the electric and magnetic field existing separately together. Why this is key to understanding quantum machinery is simply because the two-component electromagnetic energy could be disassembled into discrete components. The E field could thus be modified by resistors and capacitors, and the B field by inductors. Combined into imaginative networks, they created the LC circuit, or tuned circuit, the primary building block of electronics technology upon which all further electronic communications were constructed. The two intrinsic components of electromagnetic energy are directly comparable to the two components of quantum states of electrons affected by thermal energy. Once those components are separated, they can be utilized in separate but complementary systems, thus enabling a wholly new discharge equation for storing electrical energy. It is this equation, like Maxwell's equations, that finally enable electron-based storage compact enough and efficient enough to replace the extremely problematic non-renewable sources of portable energy storage, the extractable combustible hydrocarbons. The quantum machine age has arrived. Thank you.